distributed machine learning. The last 2 days I talked about, the day one was purely slideware on, hey, resource management is upon us, we need to do something in this space, and we can do something in this space because of machine learning. We do have some flexibility in how we execute our algorithms. For once, we often don't care about the order in which we visit the examples, and in other cases we might actually do away with some of the examples without doing much harm, so we can run on samples. On day two, yesterday, I presented kind of the minimal distributed program that you can write in REEF called HelloREEF. Some of you successfully installed the dependencies through the narrow Wi-Fi, and we talked about running it on several runtimes, and we only did it on Hadoop, on the local runtime. This was the slide of doom yesterday, where all of a sudden everyone was kind of on the Wi-Fi and we had a little bit of a congestion. So who was able to install all this software since then? Awesome. So today we can assume that most everyone has it. For those of you who don't, I published these slides of yesterday onto the reef-project.org website. So you can follow the links up on there. And given that it's about 5 people right now who didn't raise their hand, it should go smoothly in parallel to the lecture. So I want to quickly go over what we did yesterday because it was a little bit confusing because people were on different timelines. So we compiled REEF, which depends on Wake, which is our messaging library, and Tang, which we use for configuration also in Wake. So whenever you do any sort of compiling it anywhere, you want to compile Tang before Wake, before REEF. And when you compile Tang, we fetch it from GitHub. All of our code is hosted on GitHub. And then you just compile it with the standard Maven commands. So mvn is the Maven command. Oops, I'm only on this screen today. And then skip test is just for skipping the tests. Clean install means compile it and put it into the local repository. And then after some time, you get a build success message. Similarly, when you compile Wake, and also I assume that everyone who raised their hand earlier also did this since yesterday, right? Did this all? Who has not installed Tang, Wake, and REEF? That's all right. I'm willing to just move ahead with 3 hands up. So what you want to do is you fetch Wake from GitHub again, then compile it, and it will install itself into the local repository. Life is good. Last step was to compile REEF. In that case, you fetch it. You check out the MLSS branch. That is very important for this lecture because we will use functionality that's not currently in REEF master. And then you compile it and you see the same sort of printout. Now, for those of you who did this yesterday, can I please ask you to do a git pull in that folder and do the mvn clean install again? Because yesterday night and while you were listening to talks today, there were some changes in the software that will make the work today and tomorrow a little bit more smooth. So you want to pull the latest version of the software. That's what git pull does. It fetches the latest version of the repository from GitHub. And then just do the mvn clean install again. Questions? Yes? You just go into the REEF folder and then you punch in git space pull. In the MLSS branch. You should already have checked that out, right? Okay. So what we also all did yesterday, or some of you did yesterday during the lecture, and some of you did later yesterday or today, is to run it, right? So again, a quick reminder, we have 3 runtimes in REEF. The local runtime to execute things on your local machine, where each of the processes that you have in REEF is run as a local process, as opposed to a remote process. Yarn, which is great when you already have a Hadoop cluster. HDinsight is great when you would rather rent one and have someone else worry about the installation. In this tutorial, we will not use the Yarn runtime. Okay. So just a quick check. Who has been with me on running REEF locally? Who has done this? Okay, this is slightly thinner than earlier. So What you do when you run REEF, and for those of you who are not Java programmers, I want to explain it. For those of you who are Java programmers, go and read your emails for a minute. So what's happening here is you call Java, -cp stands for class path. That's basically the path at which Java will look for all the classes that you want to load. Where's the binary code? Right? That's what this -cp does. And then in the REEF examples, there's a subfolder target that has been created by Maven. Whenever you compile anything with Maven, the outcome of the compilation will always be in the target folder. And then inside of that, there is this enormously longly named file which ends in .jar. That contains all the code that we compiled. Right? And it's enormously long named because, well, the first two is just the name of the project. Then there's a version string, which happens to be 0.6 snapshot. Snapshot means it's not released yet. And then at the end it says shaded.jar. That's because we munched together a whole set of libraries into one convenient package for you. And after that, you specify the main class that you want to run. Right? That's how this enormously long command line comes together. And the class that we want to run is called HelloREEF, and it's in the package com Microsoft REEF examples hello. Right? Yay to software design with namespaces and all that. That's why it comes out to be this long. Okay, I had a couple of hands up who have done this. Have any more achieved doing this while I was explaining it? Okay. Yes? You have a question or you? Yes?
What's the branch name again?
The branch is MLSS all caps. So if you have questions like that, please always ask, right? Because you can be lost on a very small detail, and that would be unfortunate. Okay, when you run this, you will see some printout like this, and at some point, depending on how many logs you print out on your machine, you will see this, hey, there is a job completed. In this case, the HelloREEF job is completed. And some of you actually asked me yesterday, hey, where's the HelloREEF? So the HelloREEF ends up, remember, this is running on a quote-unquote remote machine. In this case, that remote machine happens to be a process on your computer, so it's not that remote. And we store all the output of those processes in a folder. So when you look into where you executed the prior command, you will see that there's now a folder called REEF local runtime. That is just a constant name that we use for all the output of anything that has been run on the local runtime. So when you, for example, to compile REEF with tests, you would see dozens and dozens of jobs that have their subfolders in there because we run REEF jobs as part of the tests. Now inside of that, you have a folder that's named after the job that you ran, in this case, HelloREEF, dash some number, and that's the timestamp of when you submitted the job. And inside of that, you have a couple of folders that all start with note dash a number, and that's just the number of virtual machines that you ran, dash again a number when they were launched, timestamp, and inside of that you have a file standardout.txt. That's where everything that this process printed to standardout in Java via system out print line ended up. We capture that in that file. So and if you cat that, you will actually see that HelloREEF was printed on the screen of that non-existing remote machine. Who has seen that? Okay, we're doing much better today than yesterday. This is awesome. Okay, and I went over all of this. And again, those slides are on the REEF website if you want to follow up. So now for new things. New things are, let's run things on the HDinsight cluster that we provisioned. In this case, it will actually run on a remote machine. HDinsight is a fully managed Hadoop in the cloud. You walk up to azure.com, which is the Microsoft Cloud website. You log in, you give us your credit card data, you click on the button, hey, I want an HDinsight cluster, and you can make one for yourself. We skipped the setting up and paying for it for this summer school because we pay for it. But this is the general approach on how you would get an HDinsight cluster. You just go to the website, ask for one. You don't have to download software, install it on 100 machines or so. So all of this is managed for you. When you submit a job to HDinsight, this has two steps. They are both done by the code that we are about to run, But it's important to understand that both of these happen. The first step is that we upload what we call the job jar to storage, to Azure storage in the cloud. That is, the code that you want to run is uploaded to some storage device in the cloud from where it can be accessed by the cluster itself. So this is, you will see this when you run it. This is the majority time that you will spend waiting for your job to run. It will say starting to copy file to Azure storage, and it will take a while because we are a little bit rate limited in this room. And then you can submit a job which actually tells HDinsight, hey, go fetch that file from Azure storage and run it. Right? Okay. So now this is the business where we need the JSON file that I was handing out on a USB drive yesterday. Who has that file? Okay, who does not have the file? That's equal amounts. Can I get one of the volunteers to quickly switch off the camera because I want to show the location of the file?
The streaming one?
Yes.
Okay. Is there something you don't want even on the recording either?
Yeah.
Can you let's just put the cover over it or something like that? Actually, just put your hand over for a second. Here, I will.
Sorry about that. Okay, so we are offline?
Not quite yet.
Not quite yet, okay.
Okay, yep.
Wonderful. So this is the link under which you will find, when you browse to there, you will get a kind of Word online which has the content of the file. Just copy that out of this into a text file and save it under a name that you can remember. The reason I don't want this on the internet is because it's quite literally the keys to the 1,000-core cluster, and someone will find nefarious purposes for uses for this. I'm sure no one in this room will, but you know, things get recorded and weird things happen.
You can almost see it in the reflection up there, but you actually can't. Fortunately, I just realized that. It's not legible.
Oh, right. You point the camera towards the audience. So if someone on the video stream can figure out that URL, then I'm fine with them using the cluster. Because it is fairly blurred. So have you all gotten the file? Who's still working on that? Who has given up? Okay, so you all have it? Can we kind of have the internet audience join us again? No one complains, then I'll move on. Okay. I'll go to the next slide. Woohoo! Yes, now I'm in the picture again. Okay, so now that we all have these credentials, what you will have to do is you will have to set the environment variable called REEF _ HDI _ conf to that file, right? It needs to point to that file. So if it's in c:\\mlss.json, then set c:\\mlss.json as the path. If you are not in PowerShell, then you will do $REEF HDI conf equals that string, right? And not do the $env colon. You look confused? So I'm setting REEF HDI conf to be this value. So in Bash, what you do is export $REEF, export REEF HDI conf equals that value. So let me type it and try whether I get it right. There we go. So what you do in Bash is probably, and the people with Macs in the room correct me, you say export, okay, without the capital E, REEF HDI conf equals path to mlss.json.
That definitely has the keys that you can see on the right there, on the left.
Ooh, that is not good. There we go. Now it's out. Well, we'll just use a new cluster tomorrow. This one might be hosed. Okay, I suppose that this line works for people on Linux and Macs. If it doesn't, then I have forgotten more about Bash programming than I care to admit. Okay, we will all know whether it worked for you with the next line, and that is again one of these really lovely long Java invocation lines. So inside of the REEF folder, you will find that there is a folder called REEF examples HDinsight. And inside of that, there is a target folder, and inside of that is this file, the REEF examples HDinsight snapshot shaded.jar. And then you run the com Microsoft REEF examples hello HDinsight class. I can do this in a terminal such that you can kind of follow along if that helps more. Let me do that. You don't see me. Let's see. So if you look into the REEF folder, there is this subfolder called REEF examples HDinsight. Oh, the highlight doesn't come through. Okay. What you need to do is java-cp, again for class path. Oh, let me do the, oops. Java-cp, REEF-examples-HDinsight, target, REEF-examples-HDinsight, snapshot-shaded.jar. That's the joy of Java development. Everything has very long names. And then the class name is com Microsoft REEF examples .hello HDinsight. Okay. Unfortunately, as soon as I hit enter, there will be lots of log output and it will scroll past. So I don't quite know whether I made a typo myself. So I'll keep it up for a minute or two longer. And don't worry, we will go over the actual code that you're invoking here later today. Okay, I will run this now and things will scroll through my screen, so hopefully that won't confuse people. That's a lovely little warning message that I put in there. Don't get confused because of that. It's because the release of HDinsight we use hasn't been released, and the server we run on doesn't have a valid certificate. That's why I had to switch off the SSL certification. Okay, what you see here is, well, you have our usual banner, and then at some point it says uploading longpath.jar to kind of longpath.jar. This is the step that I mentioned where your job is uploaded to Azure Storage, and only after that can we submit it. And when you submit an application, you get an application ID back. That application ID can be used to later on fetch the logs of the application and to query its status while it's running. You look very unhappy. Can I help? No? All good? So for example, what we can do, and that's the thing that I was coding while Dan was giving his lecture, is we can do java-jar. This is again, unfortunately, a really long path. Oops. Oops, sorry, wrong path. Examples, HDinsight, target, dash shaded.jar, dash status, and then give it this URL, this name for the application that you got, not the one that I got. I got 99. Someone must have 100, someone else must have 101, and so on. And when you run this, it might take a little while, depending on how our network connection is. You will get a printout that looks a lot like this. This is just the status of the application. In this case, it has a progress of 100%, which means it's done. It was running on some queue. Queues are the various means by which you can execute things. The very important statement that you want to look for is this final status. What this suggests is whether or not the application was actually successfully executed. For Helo HDinsight, it should almost always execute successfully, right? Because it's such a simple application. If you have an application that has a bug or anything, you will not see the succeeded, right? While it is running, and we will see this with the machine learning examples tomorrow, while it is running, it will actually say running because, well, it's not done yet. Before it is running, it says accepted, which means your application submission is accepted by the cluster for execution at some point in the future when containers become available, right? So that final status here is the interesting bit to figure out what happened to your application. Yes?
Can we use the other projector?
Can we use the other projector? I don't know. Yeah. I suppose that would help you guys on that side of the room, right? A lot. Okay, you know how to operate that. I can show my command line, yes. So, who has successfully submitted HelloREEF and seen the status completed for their job ID? Who has successfully submitted HelloREEF? That's considerably more. Okay, so this is the command line that you have to run, and unfortunately it's a long one again, to get the status of your job. Is this one of the fancy setups where I can have the second to last slide on this one?
Oh no, it's just the
Okay. Yes? It shows failed? For whom does it show failed? For whom does it show succeeded? Okay. Whom of those who say failed are on the CMU secure wireless? Are you on the CMU guest wireless? No? And it still fails? Okay, we'll have to look into that. That's wonky. It should have succeeded. We'll look into this. I'll be in the break room after this lecture for the hour between now and the dinner, and we can look into it, why it didn't work on various machines. It should have worked, but there are always things that we can't predict. Okay, so in that case, I will just show you what happens when you do -logs on the same command line. Oops. Oh, what was the ID? I need the application ID for this. There we go. So if you do logs, it will go ahead and fetch the logs of the application. And the second parameter on this call is a folder into which you want these downloaded. And just by convention, I always use the application ID. So if you go into that folder, you will find one file per container that you ran on. And if you look into this, actually the second one is the interesting one. You see that on the standard out of this evaluator, you got HelloREEF. So for those of you where it failed, please come see me after the lecture. There's something wonky going on. Okay. That's the peril of practical lectures, right? Okay. So, but you did get a printout, something like that, when you get the eventual state was failed. So you submitted the application, and then the eventual state was failed? Okay. We'll look into that. Okay. I already spoke about accessing the logs. It will be on the slides that I'll put online after the lecture. So this is how you can check for the logs. You give it the ID of your application that was returned to you by the submission, and then a folder where you want to keep the logs when it downloads them. So what this does is it goes to Azure Storage where all the logs are stored, fetches them and puts them into a local folder. Those logs are by definition only available after your job exits. So while your job is running, you unfortunately do not have access to the logs. So you always have to wait for it either to not finish successfully or finish successfully. Okay. So for the last half hour of today, I will do slideware again on some of the concepts behind REEF and what kind of flashed through and all that. And after that, I'll be here for another hour and we can work through the practical kinks of why it didn't work for some people. So you've seen on many of the slides that I used yesterday and before that, the word configuration thrown around, and there was this code that was making configurations and all that, and I completely brushed over that. Today I want to give you more details on Tang. Remember on the first day I showed you kind of the feature presentation of Tang that can turn nasty null pointer exceptions into something that you can actually parse, which says, hey, you missed a parameter. I want to tell you a little bit about the backgrounds because this will be very helpful when we look at actual code and how to write applications on top of REEF. And in good computer science tradition, we have a Helo example. In this case, it's called Hello Tang. So Hello Tang consists of an interface called message printer, which has a single method, print a message or print message, right? And you can imagine what that message will be, right? Hello world or something like that. And then we have a class greeter, which needs a message printer as a constructor parameter. Right? This is a very common design pattern. You can think of, if you want to think in machine learning terms, then this is your optimization algorithm, and it depends on a loss function implementation. Right? You want to kind of make the objective function known to the optimizer. And then in the method greet of this greeter, it just uses the message printer's print message method. Right? So far, so easy. Now, we also have an implementation of message printer, which happens to which is called Hello Printer, and in its print message, it just prints hello. Right? So there are these red things in this code, these two @injects. They make these constructors known to Tang. So Tang will consider these in the following sense. When we make a configuration, we can say bind implementation message printer to hello printer. So whenever someone asks Tang to instantiate a message printer, Tang will go ahead and make a hello printer. When Tang is asked to make a hello printer, it will go ahead and consider only the constructors that are marked with @inject. So this @inject is an annotation in Java. And then, of course, sure enough, you can go ahead and use this configuration to form what we call an injector. That's make for objects. That's how you can think about it. And say, hey, give me an instance of greeter.class. Tang will go ahead and look up a constructor for greeter. There's only one. See that there's a message printer needed. Then we'll consider the configuration given and see that, hey, the hello printer is bound to this. And then look for a constructor here, and gladly this one has no further dependencies. It can just instantiate this, and it will give you a greeter instance which has hello printer as the constructor parameter. So for those of you who predominantly code MATLAB, this is all Spanish, right? I understand that. I will go over why this is cool and what it helps with. Sure enough, this prints hello. I have a visual representation of how we speak about these things in REEF. So we have the class greeter, which happens to depend on a message printer instance. Right? And message printer happens to be bound to hello printer. The crucial bit is that these dependencies are in code. So the greeter class had in code declared that it depends on a message printer. Or your optimization algorithm states in code that it needs a loss function, right? Or your kernel machine states in code that it needs a kernel, right? And then these bindings, this isBound2 statement is in the configuration. So someone who uses this greeter can tell it which message printer to use. Someone who uses your learning algorithm can tell it which kernel to use. And I have this in a couple more examples because I understand that this is really kind of the hardest to grok part of REEF, right? Everything else is kind of straightforward processes on various machines. So we do Hello Tang in German. So instead of the Hello printer, we now have the Guten Tag printer, which is just printing Guten Tag. It looks the same. Everything else is the same. Someone else could have written this, right? This doesn't have to be even in the same code base. And then in the configuration, only one thing changes, right? Whenever someone asks for message printer, give them the Guten Tag printer now. And of course, it prints Guten Tag, and life's good. So we had this picture, and we swap it out for this picture. Nothing in the code changed, right? Because I told you that these dependency statements are in the code, while the binding statements are in the configuration. Now this is all well and good, right? We bind various implementations to interfaces. Why bother, right? You can just as well have some statement somewhere which says, if command line parameter suggests logistic laws, just code up new logistic laws, right? This doesn't make many things much easier. Let's talk about some of the things where this makes life a lot easier. French is harder than German, especially for me as I'm German. So let's talk about Hello Tang in French. In this case, I kind of got tired of writing yet another implementation of this message printer, and instead I declare a parameter. And in Tang, we use /abuse the Java type system to identify parameters. So this name here, message parameter, is now used to identify a parameter. And I will show you how that's used. We make ourselves a configured message printer, which has a message inside and prints it out. And just like before, the greeter would depend on an instance of a specific interface. This constructor depends on a value for a specific parameter. So you can now set this value to be whatever you want, and this class will pick it up. And again, this is where it becomes interesting. If you think about someone plugging in a kernel into your kernel-based learning algorithm, and that kernel having parameters, how many if-then-elses you have to write to pass the command line, right? Because all of a sudden, if it is a Gaussian kernel, you want the radius. If it is the polynomial kernel, you want yet another parameter. In this world, very little changed, right? Because we can say, we want a configuration where whenever someone asks for message printer, we make the configured message printer. Now, in addition to that, we say, okay, when someone depends on this message parameter, which we call a named parameter, because it's a parameter that has a name, we give it the string bonjour. And then from the perspective of the greeter class, nothing changed. It gets a message printer. How that thing was instantiated, whether it has parameters or not, is completely immaterial to this class. You can just write it as if you had an instance. And then, of course, it prints bonjour. So in pictures, this means we had this, right, for the German version. Now we go ahead and replace the Guten Tag printer with the configured message printer. That guy now depends on the message printer, the message parameter. And that is bound to a string. Now, again, all these dependencies are in your code, right? Your your kernel depends on a parameter, would be the machine learning translation of this. And then the configuration that your user fills out says, okay, that parameter shall have value 5. But just because you have this, nothing else in your code has to change. It's very nice to make composable software with this. And what you've seen in the code is that there are basically 3 steps in Tang. And I'm going to talk a bit about why Tang is designed the way it is. The first step is a configuration builder. That's when you write up your configuration. That's just standard key value stuff. You set keys to have a certain value. We make it so that the keys are Java classes. That way you can never mistype, because the IDE or the compiler will warn you when you use the wrong string. We also do this trick where we make all the values write once. Again, for those of you who have used Hadoop in the past, in Hadoop the configuration is a giant key value store that anyone has write access at any time who happens to get a handle onto that object. So just because you set a value doesn't mean that it prevails until your application runs. Someone else can override it. This can never happen in Tang because when someone else tries to write into your configuration, an exception is thrown and it contains both places when this value was set. So out of a configuration builder, you make a configuration. Configuration is immutable. It is pure data. This means that we can transfer it across the network without any issues. And as you might have guessed, we do Tang in the context of REEF. So the driver configures an evaluator. So the driver process makes a configuration and funnels this across the network. This is in contrast to systems like Guice, which is also a dependency injection framework in Java, which allows you to say, when someone asks for an instance of, what was it, message printer, run this little code that returns them a message printer. As soon as you allow this, it doesn't work anymore reliably in a distributed system, because this code would have to be run on a different machine. And then all hell breaks loose, right? There could be state on that machine that's different from the machine where you configured things. It's one of the biggest reasons why Hadoop configuration is such a pain to work with. And I'm not making this up, right? The people who have tried to use or have worked with Hadoop have realized this, and there are PhD theses written on the subject of whether or not you can predict out of a Hadoop configuration whether this Hadoop job will run or not, right? It's not, this sounds all very pedestrian for a distributed system or machine learning summer school, but configuring your software is incredibly complex. And it's incredibly easy to mess up and write papers with non-reproducible results. The last step in this is we use the configuration to make an injector. And the injector is the access mechanism, right? You go to an injector and you say, make me an instance of a certain class. And it will consult both the code, which encodes the dependencies, and the configuration, which encodes the bindings, to create your instance. So for those of you who have used Hadoop, I have a couple of kind of comparison statements to make. Hadoop configuration is incredibly easy compared with Tang, right? There is no like 20-minute segment in a summer school necessary to grok what it does, because it's just a key value store. The keys are strings, the values are strings, life is good. And of course, it's super ubiquitous in the Hadoop space. The tricky bit happens because there's no type checks whatsoever. So if Hadoop expects a floating point number and you put a string there, when will you get the exception, right? When will your code not run? Well, at the time when it tries to interpret that value, which might be hours from the time when you actually submit the job, right? So I don't know how many machine decades I've wasted at Yahoo waiting for that error message, right? Just because there was a typo in the configuration, someone else overrode it, something like that. It's incredibly annoying. And very costly, right, if you think about all those machine hours that are wasted. As I mentioned already, in Hadoop, it's very straightforward for anyone who gets a handle on your configuration to override parameters. So you set the memory that you want to have for your application to be 5 gigabytes, but some process in job submission overrides that with 3 gigabytes. You try to load your file into main memory, and then you get an out-of-memory exception. The configuration is not the first place where you start looking for the error, right? You will start looking for, ooh, is my file too big? Do I need to, chop it up a little different? Stuff like that. But in reality, it was a configuration. And of course, typos are not detected early. Tang, on the other hand, has a fairly strong theoretical foundation, which allows us to be very, very aggressive in type checking and detecting typos early. We do have a static analysis tool that can tell you before you even run your application whether required parameters are set or not, and whether they are within the given range, and all of that, right? So you can prove that your code won't run during compilation. If that comes back as it might run, then we still try to detect errors as early as possible. Additionally, we made it cross-language. So we have a C# implementation and a Java implementation. But right now that comes at a little bit of a cost. As you can imagine, for a project that's about 18 months old, it's somewhat immature, so some of the error messages are not as clear as we could make them, given what we have as input data. And for those of you who will write some software in REEF, you will hit that. And in those cases, please post a message on the mailing list of the form, I got the following convoluted mess where I instead expected this nice little statement. That will make our life much easier with improving the error messages. Composing configurations can be very awkward. Because of our write once semantics, if you have two configurations, let's say someone gives you a configuration for how to load the data, and someone gives you a configuration for the learning algorithm. If they happen to use the same parameter, then you will get an exception because you cannot override them. So this is awkward. Right now it's only used by REEF, so it's not as ubiquitous as Hadoop configuration. Of course, this again might change over time. Has any one of you ever worked with Guice? Okay, 1, 2. So if you compare Tang with Guice, Guice is a dependency injection framework that we initially used in REEF. It was open sourced by Google, I guess, 2008, 2009 timeframe. The main differences between Tang and Guice, they share a lot of the general philosophy of making objects through code and all that. In Tang, configuration is pure data. The concept in Guice would be modules, and modules in Guice can contain code. That is this case of, hey, when anyone asks for an object of type message printer, run this code, it will return an instance of it. As soon as you allow that, this whole remote process configuration gets really wonky, because that code could use local state that's local to this computer. Let's say it looks up the class name in a file, and that class name is not in that file on the other computer where you want to run it. And then you are again in this mess of having to run it to see the exceptions. That was the main reason why we decided to go ahead and build yet another dependency injection framework. The second reason is Tang generalizes across languages. So what we do is we extract all this dependency tree that is encoded in code into data, and we do this right now for Java and C#. There's no reason why it wouldn't work for C++ or Python or maybe Ruby. We just haven't done that yet. This allows us to do things like you have a Java job driver that configures tasks written in C# and vice versa, and we can check the errors early. Okay, so how do we use Tang in REEF? The first thing how we use it is we provision all of the REEF APIs through Tang. So if you want to have access to any of the APIs in REEF, the way you do this is you write a constructor and you depend on an instance of it. You just have a constructor parameter with an instance. This means that for all the APIs that you don't use, you don't even see them. That makes code a little cleaner, especially at the beginning when you don't interact with too many of the REEF APIs. The second part where we use REEF and where you will use it in code is to configure REEF itself. Applications bind their own implementations for all the event handlers that I was mentioning earlier, right? So when start time happens, that event is fired to an event handler that's registered in Tang. When you submit a task, what you actually submit is a configuration that contains a binding between the task interface and your task implementation. So we use Tang both to expose REEF APIs to applications and to expose application implementations to REEF. This interdependence makes very interesting things possible where REEF becomes very extensible, fairly straightforwardly. Lastly, we use it for contexts. That's another of those words that appeared on the slides. I never quite explained it well enough, and I want to do this for the last 10 minutes of today. And we had this example code for HelloREEF. By now, these configuration statements make some sense, right? Because we created a task configuration here with a builder, and at the end we say build. And we bind the task interface to an implementation. And then we submit a context and a task. So the task part of that should be fairly clear by now. What we do is we tell REEF, hey, when anyone asks for a task instance, give them hello task. If anyone asks for the name of the task, what we call it the identifier, tell them HelloREEF task, right? So this is just a configuration that configures REEF to run a specific task. But there's this other thing called a context, which is also submitted as a configuration. And I want to talk a bit about that. So contexts in REEF are a way for an evaluator to hang on to state in between tasks. Think about you run a straightforward implementation of gradient descent. You submit a task that computes gradients, that sends a model back, gradients back. Some master computes a new model, and then you want to submit yet another task to compute the next gradient. It would be very convenient if you in between could hang on to the training data, such that you don't have to load it from disk again and again, right? That was the 30x speed up that everyone who improves upon Hadoop claims, not loading things from disk. So that's one aspect of Tang, of context. The other aspect is contexts can be stacked. So you can have more than one on top of each other, and the semantics are that the topmost context has access to everything underneath. Or in the case of a task, which is always the topmost thing running on this stack, a task has access to all of this. So think about the following. You have a context that contains some training data, and unfortunately I'm not sure whether you can read this. This text is a context that contains training data that's sitting on this evaluator. But it doesn't contain the training data yet, it's just a placeholder. Now we submit a task to this that shall load some data. And while it is running, it is filling up the context with actual training data. Now when that task is done, the context sticks around. And all the kind of in-memory variables or files on disk or whatever this prior task created, they are still there. Which means that if you now go ahead and submit another context that happens to contain a model, and then submit a task to it, which shall compute a gradient, that task has access to everything underneath it. So it has access to the training data and to the model. So I was talking about that Tang is used for contexts. And some of you might guess how we do that. I have to tell you a few things in Tang that are just true that make it so much easier. Objects in Tang are always singletons. So if, for example, multiple places in your code depend on the kernel, they all get the same instance, right? That's one truism. That's true as long as all of these objects are instantiated on the same injector, right? When I go to an injector and I ask for an instance of your learning system, and inside of it there are dependencies which ask multiple times for the same instance, let's say the kernel, they will all reference the same object in memory. We will not instantiate objects twice. Now, injectors can be forked, which means that you take an injector and all the objects that have been instantiated right now, create a copy of it with additional configuration. So when someone asks for an instance of an object that was already created at the time this thing is forked, they will get the same thing. They will get the same object as before the fork. If someone asks for an object that wasn't part of this, a new one will be made. Now with both of these things being there, we can say that contexts are injectors. So if you think about what I said about when you write your code and you have dependencies on your constructor, those are met by some injector. And if that injector happens to be the context, then you can think about the code saying, hey, here's a compute gradient task. It depends on training data and model. And both of these dependencies are met by the context that it runs on. Right? This particular nuance is not incredibly important to know. What you need to understand when you write REEF applications is you can depend on things that are in the context, not by doing a get or any kind of key value store operation, but by just depending on instances of these objects in your constructors. And we will go over this in gory detail tomorrow when we actually implement a batch gradient descent. Okay. At this time we have 6 minutes left, And I want to do what I did at the end of yesterday's lecture and walk you through the code, but now with the knowledge about what's going on in terms of Tang and contexts. So, let me just, you don't see that yet, right? Not that I'm giving away secrets again. Okay, there's some way to make this more visible. This is big enough, I hope, for the last row to see. Okay, wonderful. So this is the class HelloREEF no client for those of you who have installed an IDE and want to look at it. So we have this main function here, and this is just like in any programming language in Java, there is a main which is executed when you run this class. It fills out a configuration, in this case the local runtime configuration. And again, the runtimes in REEF, local or HDinsight or yarn, they just bind interfaces to implementations. REEF depends on certain things, like run something remotely, and the runtime provides an implementation of that interface. So in this case, we want to use the local runtime. The local runtime has a parameter which tells us how many threads or processes do we want to run at most at any given moment in time. In this case, 2 is enough, 1 for the driver, 1 for the one evaluator. And then we call this run HelloREEF without client. I'll go over why it's called without client tomorrow. What we do here is we fill out a driver configuration. There's a little bit of boilerplate here, but what you see is we give the driver a name. Right? That's the string that you saw in the folder name, for example, when you run this on the local runtime. That's the name of your job. It also shows up when you do the status operation. It shows up in the logs. That's what uniquely identifies your job. For some of the code we'll use tomorrow, we conveniently put your username there, the username on your local machine, because if we all submit a job to the cluster with the same ID, it will be very awkward for us to figure out who submitted which one. Right? So this is the way how you make things identifiable. And then we bind 2 things. We say when driver started happens, we want to have this class receive the message. Right? This is a Tang binding of the interface or name parameter in this case. Driver started, that's the destination for the start event. We want an instance of HelloDriver.startHandler to receive that. When evaluators get allocated, we want an instance of HelloDriver.evaluatorAllocatedHandler to receive that. And again, this is Java and names tend to be long. Okay, so now let's look at this Hello driver. Oh, sorry, I didn't tell you yet that we make ourselves a REEF instance before this. And a REEF instance is this class that you can submit jobs to. And we make it by making an injector of the runtime configuration and then calling for an instance of, there's actually a bug or slightly not nice code, and asking for an implementation of REEF. Right? So this runtime configuration could contain a binding that says, hey, when someone asks for a REEF, give them the REEF local implementation. Right? This way we can make this code very generic, and the only thing that the user of this HelloREEF needs to change when they want to submit to, let's say, HDinsight, is provide another runtime configuration. Okay. And then on this REEF object, there's basically only one method, which is submit, to submit a job to the cluster. And this submit method accepts a driver configuration. And the driver configuration tells us everything we need to know about what to do when things happen. And if you look onto all of the events that driver configuration has, there is any number of events that you can listen to. You can listen to on driver stop, on task completed, on task running, on evaluator allocated we already listened to, driver started we listened to, and so on. Right? And you can see at the type back there, that's a nuance of Tang that I didn't go into, what is optional and what is required. Right? So you need to give us a driver started handler. You need to give us an identifier. You don't need to give us a handler for the stop event. right? That's the default behavior that it was having on the slides yesterday. Okay. Now let's look at the actual driver. So the driver code is fairly straightforward. So I mentioned when we were going over the slides that the way you get access to REEF features is to depend on them in your constructor. In this case, the constructor depends on one thing, and that's an evaluator requester. That's the class through which you can ask for additional evaluators, right? You can do so at any point in your driver, in any class. It's not required that it is in some sort of main or that it happens at the beginning of your computation. You can always ask for more evaluators. This is important, for example, when you see load spikes and you want to ask for some more machines to act on them, or when you see that machines fail and you want to run stuff on different machines. Then the start handler uses this guy. Oh, we don't have the, give me a second. Why is it not moving? I can move the cursor, but I can't scroll. This is awkward. Okay, somehow we don't see the content of the start handler. Give me a second. The presentation mode. I was looking for this button. Okay. Wrong. Oh, come on. There we go. So the start handler then uses this requester to just ask for one evaluator of only 64 megabytes of memory, right? And then that's it. That's all that the start handler ever will do. It will just ask for that one evaluator that we want to run on. In other applications, it might do a lot more, right? It might figure out where's my data, which machines do I want, all of that stuff. But for HelloREEF, that's all it needs to do. And then in the allocation handler, all we do is we do create a context configuration. In this case, the context is empty. It just has a name. And we create a task configuration where we give the task a name again. This is again for identification. REEF itself doesn't depend on what kind of name you give here. You can always use the same. It will just make it nearly impossible for you to read your own log files because they will all be called the same and it's kind of tricky. Then we set the task to hello task and we submit this context and task for execution on the evaluator. And that's all there is in the HelloREEF driver. There's this try catch around here where we catch the bind exception. Bind exception is thrown by Tang whenever anything goes wrong with building a configuration. So when you try to set a value that's already set, when you forget to set a value that is required, all of those will trigger a bind exception. They shouldn't happen at runtime, right? But it's incredibly useful at debugging and development time to have them. And in REEF, you will often find this kind of, when we catch it, we immediately bail on the whole application by throwing a runtime exception. Okay. Let me go back to this and quickly do a summary. Woohoo. Okay, so what we've seen yesterday and today combined is the simplest program that you can run on REEF, which is HelloREEF. Get a single driver that goes ahead and asks for a single evaluator, submits a single task to that, and that task only printing one thing. We went through compiling REEF. We went through running all of this on both the local and the HDinsight runtime. And again, I'll be in the other room for the next hour to help those where it didn't work on the HDinsight runtime. I hope that I gave you a glimpse of why Tang and why it's cool and what it does for you. If you're not convinced, that's okay. You still have to live with it for REEF. And I showed you how we do context and why they are useful. With that, I just want to say what we do tomorrow. Tomorrow we actually do some machine learning. We start by introducing the group communication primitives that we have in REEF for broadcast and reduce. And then we will look at a very simple learning algorithm, namely batch gradient descent, with a fixed learning rate and a fixed number of iterations. So nothing that you would do in practice, but pretty close to actual machine learning. Thanks.